Welcome back. We talked about in the last section how we can define equilibrium as when the rate of the forward reaction is equal to the rate of the reverse reaction. Macroscopically, it looks like nothing's happening, but on a microscopic level, we have dynamic equilibrium. Products are constantly forming reactants. Reactants are constantly forming products. So how do we quantify that relationship? We're going to introduce our favorite thing, the generic equation. We talked about this in kinetics, and now we're going to talk about it here. We've got AA plus BB, but now we're going to talk about equilibrium, going to CC plus DD. Right? The little letters are the stoichiometric coefficients, the big letters are the actual chemicals themselves. And what we're going to define, and you're like, why would you define this? Because a lot of really smart people figured it out a long time ago. So we're going to define this thing called capital K. And we're doing that really just to confuse you between the lowercase k, especially since your professor has bad handwriting, of the last chapter, which was our rate constant. No. Here we're talking about capital K, which we're going to define as the equilibrium constant. Some people will write an EQ down here. It's not required. It's optional. Means the same thing. K, KEQ means the same thing. We will put several other subscripts on there as we go through the class. Some A's, some F's, some C's, some P's. And those mean different things in terms of here's a specific situation of K. But this K works for all situations. It's just a definition based on a balanced chemical reaction, and it is this, that the equilibrium constant is defined as the concentration of C times the concentration of D. So the concentration of your products raised to the power of their stoichiometric coefficient, so little c, little d there, divided by the reactants. And so we're going to take concentration of A times the concentration of B raised to their stoichiometric coefficients, little a, little b. That is just the definition of the equilibrium constant. And the amazing thing is this is constant, regardless of initial conditions. So just to make an example, let's say I have a reaction and K is equal to 50. It turns out if I start with all reactants, A and B, all reactants, let it react, come to equilibrium, I calculate K at equilibrium, right? This is only true at equilibrium. Right? So I'm going to even add. If I calculate K, it'll be 50. I start with 500 times as much A as I have B. I let it run and come to equilibrium. I calculate K, it'll be 50. I start with A and B and C and D present. I let it come to equilibrium. I calculate K, it'll be 50. I start with only C and D. I start with only products, right? Which really stretches that definition of reactants and products that you're familiar with. I start with only products. I let it come to equilibrium. I calculate K, it will be 50. Okay? Remember, our definition of reactants and products, reactants are the things on the left-hand side of the reaction arrow. Products are the things on the right-hand side of the reaction arrow. Reactants and products are not reactants react to make things. Products are the things you make. Because products in equilibrium can make reactants. Products can react to make reactants. C and D react to make A and B. Okay? So reactants, left-hand side, products, right-hand side. That's the only thing it actually means. So this is a really, really cool concept. If no matter what you do, you get this thing that's a constant. That constant will allow you to calculate all sorts of things. And that's what we spend the next 8 weeks talking about. So let's just practice a few just to get the form down. We're going to write down the equilibrium constant for this reaction. Looks like a very complicated reaction, but equilibrium constants are cool. You can always write them from a balanced chemical equation. Unlike our kinetics, we couldn't write a rate law from a balanced overall chemical reaction. We had to have mechanisms, or we had to do it experimentally. But here, equilibrium constant, you don't have to know what's going on in the details. That's very nice. And we're going to write K is equal to the concentration of NO2 to the 4th, the concentration of H2O to the 6th, over the concentration of NH3 to the 4th, times the concentration of O2 to the 7th. Okay. And then you put in those. You wait for equilibrium, you put in those numbers, you will always get the same K, no matter what you started with. How about for the next one? Again, we've got these double arrows indicating equilibrium. And so we're going to write an equilibrium constant, K is equal to the concentration of NO squared, the concentration of Br2 to the first, over the concentration of BrNO to the second. So just each thing in there raised to the power of its stoichiometric coefficient. Very, very simple, very easy to do. All right, this is your turn. What is the equilibrium constant K for the reaction methane plus hydrogen sulfide makes CS2 and H2 gas? Go. Okay, what did you come up with? Well, hopefully you just looked at it and say, well, it's always products over reactants. Okay, always products over reactants. So my products are CS2 and H2. So that's not it. That's not it. And then raised to their stoichiometric coefficient. CS2 should have a 1. There's a 1 there and a 1 there, so we're good. H2 should have a 4. It doesn't have a 4. It does have a 4 there, so we know it's not that one. But let's check it just to make sure. CH4 has a 1, and H2S has a 2. All right, so that tells us that D is the answer here. That's our equilibrium constant for that reaction. Cool. All right, so let's go ahead and do some calculations with our equilibrium constant. We're going to go ahead and calculate the value of the equilibrium constant for this reaction because somebody ran an experiment and they measured the concentration of all 3 of those species at equilibrium. That makes it really easy. When you have equilibrium concentrations, it's really easy to calculate an equilibrium constant. Let's go ahead and write the form of our equilibrium constant. It's going to be the concentration of N2 times the concentration of H2 cubed, right? We got to raise it to that power, over the concentration of NH3 squared. And that is going to be our rate constant. Now let's go ahead and just plug in those numbers. Notice what I'm about to do when I use generics. When I say the concentration of N2, I use those square brackets because those square brackets mean concentration. As soon as I write an actual number that has a concentration unit on it, I'm going to use parentheses because I don't need to specify its concentration because I'm writing a concentration. So N2 is 0.85 molar. H2 is 0.0031 molar. I'm going to cube that. And then I've got my NH3, which is 0.031 molar, and I'm going to square that. Now, if you look at that one, right, you can plug those numbers into your calculator, and we'll get that number in just a second. But I want to pause and think about the units for this for just a moment. If I were to do this, what units would I get? Well, I'd get molar times molar cubed divided by molar squared, which is molar to the 4th over molar squared. And so I'd get molar squared as my units for this K. I'm going to go back one slide, or 2 slides, and look at these guys. What would I get? On the top, I'd get molar to the 10th. On the bottom, I'd get molar to the 7 plus 4 is 11th. And I'd get an overall unit of molar to the -1, or 1 over molar. On the bottom one, I'd get a unit of molar. Those aren't units that make sense to me, right? Molar to the -1, and over here we've got molar squared. And how come K can always have these different units? We ran across that in the rate constant. We said that depending on the order of the reaction, the overall order, K would have different units. But that gets a little tedious here, and there's other good reasons. So what we do when we're talking about equilibrium constants is, it turns out we are not writing the concentration of N2. What we're actually writing is the concentration of N2 divided by a reference concentration. And what does that do? It says, hey, let me take my 0.85 molar. So let me clarify this. When we write the concentration of N2, what we're really writing is the concentration of N2 over a reference concentration. What reference should I pick? It's a reference. You can make it up. Everybody picks 1. Why? Because if you divide 8.85 molar by 1 molar, it doesn't change the number, but it gets rid of the unit. There's other good reasons for this. We're not going to go into all the great detail. It has to do with activities and things like that. But for our purposes, what that means is when we're writing down these reactions, we write these square brackets, we talk about concentrations, but when we write out the actual numbers, we leave off the concentrations as long as we're working inside this K. When we do find final concentrations, we have to bring those units back in. Now, we could write this K as N2 divided by reference concentration times H2 divided by reference concentration cubed divided by NH3 divided by reference concentration squared. But no one ever does that. It's like this little implicit secret. Hey, don't forget to divide by your reference concentration. No one ever writes, make sure to divide by your reference concentration. So we're not going to either. We're just going to follow what the rest of the world does. But the reason we don't use the units in there, the reason K ends up being unitless, is because every one of those concentrations is actually divided by a reference concentration. When we calculate something with that, we have to multiply by the reference concentration to get our units back. Again, no one does that explicitly. They just kind of do it and talk about it. So that's what I'm going to do. So what do we actually get for K is not this funny thing with all sorts of units on it, but we get that K is 0.85 times 0.0031 cubed divided by 0.031 squared. K has no units. You just plug that into your calculator, and you should get 2.6 times 10 to the minus fifth. No units. One of the very few numbers in chemistry that has no units is the equilibrium constant. pH is the other one that we run across somewhat frequently. So 2.6 times 10 to the minus fifth, just a number. We'll talk about the meaning of that number as we go on in the class. All right. So that is how we calculate our K value. I feel like there was something else I wanted to say about that, but there we go. That's our 2.6 times 10 to the minus fifth. All right, so we just calculated the value of the equilibrium constant for the reaction ammonia falling apart into nitrogen and hydrogen, and figured out that it was 2.6 times 10 to the minus fifth. What I want to know now is what's the value of the equilibrium constant for the reverse reaction? We've got N2 plus 3H2 goes to 2NH3. So go ahead and calculate that, come up with the value of the rate constant for the reverse reaction, and then check in. What'd you come up with? Well, you could plug all those things in, absolutely, and you'd plug in the concentration of NH3, square it, divided by the concentration of N2, divided by the concentration of H2 cubed. But let's look at it. For the forward reaction, we had the concentration of N2, concentration of H2 cubed over the concentration of NH3 squared. For the reverse reaction, we had the concentration of NH3 squared over concentration of N2 times the concentration of H2 cubed. How are those two things related? If you look how they're related, it's just 1 over. So K forward, let me actually use the word forward, is just 1 over K reverse. And so we can actually just take 1 over 2.6 times 10 to the minus fifth. And that would be how we get our answer, which would be 3.8 times 10 to the fourth. Like I said, you could have plugged it in and just done the numbers there, or if you recognize that, you can just do 1 over. And we'll explore more how K changes when we manipulate reactions later on in some of our work. All right, that was apparently our last slide. I didn't realize that was our last slide. So there we go. I hope that was helpful. And in our next part, we're going to talk about how we can do this when we're talking about pressures. Is it the same equation? Is it a different equation? And we'll see how that looks. Thanks.